Hi, it's Terry Denery of the MathWorks. So in this video, I want to talk about the idea that this PID algorithm really can be kind of, I'll say, morphed or kind of adapted to be very much a feed-forward approach. Okay, and I certainly would argue that that's part of its success, but its primary success is this idea that it is a rubber band, and it essentially kind of connects what we want the real system to do to the idea of, of, of what we want it to do. And that they're beautiful in their ability to kind of adapt to what I'll call the impossible request, like responding to a step function. And that certainly we're very good at judging how reasonable that response is. And we also have the means by adjusting KP, KI, KD to tune it to be as reasonable as we can get it to be. Okay, so anyways, I'd say that the reason that this is important to me is that I want to address this idea that we do not need feed forward. We do not need to use what we know um, to get a system to move the way we want it to. That I think that seems silly to me to not use what we know. Okay, and it's possible, you know, that we're just not in the habit yet of kind of doing what I think makes a lot more sense, being reasonable, using what we know about the mechanics, electronics, and so forth to get it to do what we need to do. But there certainly isn't, I'd say, this paved path um, for that approach that exists yet. That the paved path is using PIDs, right? So in a way, you could say I'm saying let's kind of disrupt that a little bit, right? But at the same time, let's tip our hat and say that that path got paved because it really did work pretty well. And then part of that was that it can act like a feed forward approach. But I'd say that the problem with kind of believing too strongly in that is that it can act as a feed forward approach for, I'd say, a small subset of systems, and it's mostly these systems that are linear in nature, like F equals ma. You just integrate it twice, and you got position, A that is, and the simplicity of a single mass. And the real machines are nowhere near that simple. Okay, so here goes. So let's go ahead and kind of consider the approach. So this is the model we used in our previous video, but I've elaborated to be a little bit more. The plant model is almost identical, although it looks like it's more complicated. But the truth is we're still taking force, dividing it by m, and integrating it twice to get both velocity and position. And I'm simply reporting position, velocity, and acceleration as the output of this plant model. Okay. Now, the other thing is I did add a feed forward component, all right, and you'll see feed forward for a simple mass constrained to movement in one direction as subjected to by a force is really a pretty easy feed forward to do. That I want it to move in a certain way. I define that movement by position, velocity, and acceleration, and I simply pick off that acceleration multiplied by m. That's my ideal force to achieve the movement that I want. All right, so anyways, I think I'll begin by coming in here. All right, and you'll see what I've done is I've taken this feed forward piece and I'm multiplying it by gain. Let me make that gain 1. And I've taken this feedback piece and I'm going to multiply that by 0. So we're going to see purely feed forward in this simulation we're about to run. Okay, now the thing that's real interesting to me is that the calculation is still being made on feedback. And what I want to prove is that this calculation, even though it's not being used in this control algorithm, but it is going to be calculated so that we can compare with what is being used, which is the feed forward piece. Right? So let's just open up this scope and we'll run it from here. Right, and so the yellow line will be our feed forward, and the blue line will be our feedback, our PID calculation of commanded force. Okay. And clearly, it's for most of the part of the simulation, it's beautifully on top of what the feed forward calculation is. All right, and I want to just give a little bit of explanation of how that happened. And one thing you'll notice is that I'm actually doing velocity control, as I'm commanding based on the second signal. So the order is position, velocity, and then acceleration. I'm not even pulling it out. Okay, but I'm operating on velocity. Okay, and ultimately I'm doing position control, but if that velocity is consistently defined with position, meaning that it is the true derivative of the position, that that should work, right? And there's a little bit of an assumption that you got the initial condition defined correctly, which we do. Okay, and the reason I did it was very, very convenient for what I wanted to do, right? And so um, I labeled these signals. So the command is I'm calling v in plus one, and then the feedback I'm calling v in. Okay, and I think this is appropriate. Kind of getting into this index notation that we use with discrete signals all of the time. That n plus one is essentially the future. It's that next time step that we want. Okay, and that if we're doing everything right, our command signal is the future. And what I mean by doing right is that we're applying the appropriate force on the system, and therefore, by the very nature of it being a mass subject to the force that we're going to apply based on this calculation, we're going to be real close to v n plus one for our next time step, right? And so then, but anyways, this difference, vn plus one minus vn, and then my kp, my proportional gain, I make it equal to 1 over delta t, right? And I'll just kind of show that in my capture of the velocity signal to be kind of consistent with all of this, you'll see that I am discretely assessing it and that my sample time is delta t. So I think that's pretty reasonable explanation of how I did this, and you'll certainly see that ki and kd are both then equal to 0. All right. And what I want to show is that this is still kind of an open loop calculation, and with regard to position, we end up doing awfully well. Again, this is all based on feed forward. There is no feedback to kind of close anything. And that's why we will see, just use this to a little bit of a drift. And I think you can kind of see it. I think after 10 seconds, it drifts about 5 millimeters, which may or may not be okay, right? Um, all right. And so I'm going to kind of do a few things right now. I want to go 0 on feed forward and 1 on feedback, right? And let's run it again, and I'm going to just observe it from the scope this time on yellow being command, blue being response. And you're going to see what we love about feedback systems is that if there's any error at all, they're really, really good at driving that to 0. Okay, and so with that feedback, we don't get the drift. All right. And let's see. I guess I'll show this next. All right. But and this is really important. Okay. And there's a few things to talk about here. And I certainly don't want to argue that a good controls engineer would allow this to happen. Okay. But, in the previous, well, let me say this. Our time step is 1/1000th of a second. So that means our gain is equal to 1,000. And we saw in the previous video that we got pretty good control with a proportional gain of 100. So this is a really, really high gain actually for this system. All right. And what it really means is that it is overshooting substantially on restoring force. You know, and it means that I could be off by, like, let's say, a small fraction of a degree, but I'm multiplying it by 1,000, and therefore it's a pretty high force that is being applied to restore, right? And it means that we're continually overshooting. It might even be this very small fraction of a degree, but our actuation just goes back and forth at really high values, right? And of course we don't like that. There all kinds of things that probably just innately bother us, but certainly the idea that you're applying a force that's proportional to current, and then that current multiplied by voltage is essentially the power being consumed. I don't think it's super hard to convince yourself that you're consuming an awful lot of power with this approach, right? And certainly with a tool like MATLAB and Simulink, we can put those electrical actuators in there, but in those hydraulic pneumatic actuators too, and we can observe actually how much power consumption that really does represent. But I can tell you it's enormous. Okay, so anyways, we do have a little bit of a problem. All right, and so now I want to go back to kind of where we were, and so I'm zeroing out feedback. It's all being delivered by feed forward. Um, I'll hit run again. We'll see, I believe, a 5 mm drift, which we do. Okay, and we'll see this minimal power consumption. This is the best we can do. All right. And I now do want to kind of address a few things that we didn't really get to, which you may have noticed when we first looked at this. All right. And clearly there's a problem right here. All right. And I don't think it takes too much to kind of consider that, well, that's a very discrete, singular point, where essentially velocity stops, that we're supposed to to reach our target and no longer move. Okay, and so why do we have this? Well, the fact that PIDs work only if there is error kind of reflects kind of this really important nature to them, which is that they always have a little bit of a lag. Okay, and that this lag, is what allows essentially a reasonable response to take place to a discrete, or a step change. The step changes occur instantaneously. PIDs say, hey, hold on, so let's slow it down a little bit. And that they're able to respond, again, in a reasonable way because they insert a transition time to allow things to happen, right? And that by their definition, nothing will happen until we actually see that there is a problem. That's what feedback is, right? And so I won't try, well, certainly I'm not what I call a formal controls expert. I might consider myself a formal mechanics and electronics and kind of, expert of representing, electromechanical machinery. But there's certainly a real depth to controls knowledge that a lot of my customers have and a lot of my colleagues have at MathWorks that helps me appreciate what they do. Okay, and I think that go talk with them and they'll give you a little bit better explanation of why, my blue line, which is my response, I'll say zigs when the command itself zags. Anyways, I like that. One zigs, the other zags. Okay, but it kind of goes the other way at this very kind of special, unique point, right? And so as I looked at this the first time, I was really baffled by it. I was even concerned to go, how am I going to do this demo and this thing's just not working? But I realized, oh, wait, there's something really interesting there, right? But one of the things that really bothered me was, well, why do I get it here, but I don't get it here? Well, it turns out you get it here too. And if you look real close, you'll see that it just kind of goes in the right direction on this one. So anyways, the point being is that, well, there's two. I think I'm going to take one more step on this one, and explain that this idea of, well, why does it even work at all? If I let's see, go do this again. Actually, before we do this, I'm going to do one more thing. I'm going to make things harder, right? And so my period now will be 0.1, period of transition. So I'm going to really accelerate. So let's get back to this view. The movement from this point to this point, we're going to do it in 1/10 of a second this time. And yeah, this is the remarkable thing of feed forward. it gets you through that transition, great. But when you get to the finish line, things aren't exactly right. And so then you go in here and kind of do it the other way, which is essentially PID is doing both feedback and feed forward. And we hit run on this. And again, it does it beautifully. Okay. And okay. And so my argument is for this mass, which is going to move according to the force applied divided by its actual mass, integrated twice, and you'll essentially understand position versus time that it will take on. That this is really what I'm proposing, but what I'm saying is that if I do it with feed forward, with a real basis in the mechanics and electronics of the system, I can be much more elaborate and therefore much more useful, okay, than simply F equals MA, all right? And so then this last point I did want to get to, and is the idea that, well, why don't I do it with position control, all right? And so I'm going to take position now, and I'm going to feed back position here, and now I'm going to make my KD 1 over delta T. Okay, and I'm going to zero out my KP. And I'm going to hit run, and all, I won't say, and I'm afraid I'm going to use a cuss word, but let me say all heck breaks loose. Okay, and I'm going to just say it doesn't work, and I'm going to say that the way I was doing it before, there's a real benefit in the purity of the calculation, that I'm not applying numerical integrator or differentiation here. I am formulaically assessing individually all three, position, velocity, and acceleration. I'm using that. And therefore, I have a much better um, evaluation of the derivative when I measure it from my own velocity as opposed to allowing this combination of transfer function and du dt block to do it for me. Okay, and so I'll say that's the difference, and that's why this one goes unstable, right? And so where I want to get to with this video is to, again, praise properly, PIDs for what they do. Okay, PIDs fundamentally work because they are rubber bands, right? That whatever um, speculation my feed forward algorithm might have, that this is the system and this is its state of motion, feedback ensures that that you better get that right. Okay, and if you apply feedback properly, I believe you can get that right. You can get that state of motion. Okay, and that's one thing that's really good about PIDs. But I think why they did work so well for us over these last, let's say, 100 years or so, is that they actually really did do both pretty well. And the problem with kind of using them the way that we have is it really did kind of limit us to applying controls to systems that we believed that we could control. And they were systems with a simplicity that was close to, a simple mass moving in a single direction as subjected to the force that we're controlling to get the motion that we want. Okay, and that if you look at a lot of robotics or a lot of automation equipment, quite often you're seeing this. It's all very Cartesianal. All right, and the reason they do that is so that it can have that simplicity of essentially F equals ma. All right, and I'd say that what I think is exciting about where I see this going is that machines can be anything, and that their ability to be sketched up in tools like SolidWorks and CATIA and Pro Engineer and Siemens and X, but these beautiful CAD tools that ultimately lead to production of these systems according to what you drew and materials that you chose to essentially have the masses and inertias that we anticipate early because we can draw them up in CAD tools. But to bring that in and to very automatically kind of create the right simulation model uses the basis of a control, and then use tools like SimWise and Motion Genesis to get something onto an embedded processor that does this, whatever you want to say about this, but does this, you know, anticipates the force required based on the response you want. To do that for much more complex machines, I think that that's not far from where we are right now, and I think that it'll be exciting how that will change the way that machines can be designed to ultimately perform better. So, anyways, that's what's interesting to me. Thank you.